Hello, my name is Frederic Pouillot, and I am the director of the Clean Energy Institute of GPEX. In this video, we're going to talk about a new tool that we have developed, which was designed in order to help car users and fleet managers to evaluate the economic performance of electric vehicles. Not only cars, but this could actually apply to trucks, motorcycles, and any type of internal combustion engine that may be converted to electric. This course is a free course, and it can be accessed to the URL displayed here. We'll also provide in YouTube you'll see a link to the website so that you can directly click on that. The software can be downloaded free of charge. It was designed, actually we designed that in Excel, but then we decided to make that available to anybody. So we used OpenOffice, which is a free open source software. And because the software contains some advanced functionality, we actually had no choice but to use macros. So if you want to be able to use in OpenOffice the advanced functionality, you'll have to allow macros. If not, it will still run without macros, but advanced features such as the sensitivity analysis will not work. So now let's download the software. In order to do that, you can just scroll down until you see under the first section the link to the software. And I'm using here Google Chrome, which automatically puts the downloaded application there on the bottom left. In other applications, you can decide where you're going to save the software. I would suggest you actually copy that onto a preferred location. So we're just going to open here the software by clicking on that item. And I want to point out that if you did not have OpenOffice, you can download that for free from openoffice.org. Here it's telling us that there are macros which indeed can be hurtful if you don't trust the source. And actually, in this case, I'm not going to show right away the advanced functionality. I'm just going to disable the macro. So just going to run it like that. Let's start by giving you a quick tour of what the software does. The software was designed to allow you to input data on the two different types of cars to compare, to input the usage, and based on that, and based on various conditions for the cost of electricity, the cost of fuel, cost of batteries, type of batteries used, as well as under the cost analysis here, you can enter, of course, the different operating cost, as well as initial incentives or freight charge, and so forth. You can then also enter the assumed value at the end of the ownership. In the financial analysis, you can specify whether or not the car is going to be financed or leased over a number of years, enter the interest rate. And we have initial database of vehicles. You can actually change that. You can enter your own there if they're not there. Advanced functionality will actually have the ability to provide more, but to start with, that's what we have. You can also do an emission analysis to evaluate how much tons of CO2 you'd be able to reduce, and if there was any type of incentive, what would be the impact. And in the end, it shows the financial summary of basically the most important financial ratios, such as your savings over the life cycle, the net value of those savings as of year one, the internal rate of return and benefit costs. It shows here if you're financing the car, for example, in red, that's your electric vehicle versus the internal combustion engine vehicle. As you can see here in that particular context, the electric vehicle is initially more expensive, and through the years your ownership costs actually are reduced. And here it shows over the life cycle basically what your total cost for the ICE versus the EV, and we've grouped that here by capital cost in blue, which is the most important, operating cost also in lighter blue, and your battery costs actually here, which are normally a part of the car, but we broke that down to actually reduce the initial cost so that we can distinguish between those two parts. And the cash flow graph shows basically your savings over the years. In the next section, we're going to show you how to compare two cars using the model in more details. Let's assume that we want to compare the Nissan Leaf to Canada's most popular car. The Globe and Mail, one of Canada's trusted newspapers, provides an article here that suggests that in 2012 the Honda Civic was at the top of the list, so we'll use that as a base case. According to this website, the Honda Civic 2012 is about anywhere between $15,000 to $27,000. So we'll just use a, let's say, a $16,000 price to start with. The first thing I'm going to do here is just save that file for that particular scenario. And I'm going to call that EVScreen Leaf versus Honda Civic Scenario 1. The case study will be performed in the Canadian context. We'll start with Canada's largest province, Ontario. So you could change that and select other countries. We have some pre-built. So the currency is Canadian dollars. Note that if we change that to, let's say, Japan, then it will change the currency to the Japanese currency, and so forth. Or in Europe, we change that to the euro. So we'll just leave that as Canada. And for the currency rate, as of the end of 2012, we have an exchange rate which is pretty close, so we can use that particular rate. We'll enter the name of the car that we're comparing, and we'll enter the initial value for that car. The Nissan Leaf is our proposed case, but we could select from the built-in database, and that list is populated automatically from the vehicles database, which is here. So if I wanted to have my own, I could just enter it here and it would show on that list. Then we'll enter the usage information. So in this case, we'll assume 40 kilometers travel each day in the city, and about 25 on highways. And on the weekends, a total of 60 kilometers with about 50 kilometers on a highway and 10 kilometers on the in-city driving. So that gives us a total distance traveled, which is calculated here, of 20,000 kilometers in that particular case. We'll assume a period of ownership of 10 years. And by the way, you can navigate here in OpenOffice from cell to cell by using the tab key. In Microsoft Excel, it's the enter key, but here it's the tab. The cells in white are protected, so you cannot change them. In terms of period of ownership, there are two considerations here. One is the average period of ownership, and At the current time, for those type of vehicles, it's about 11 years. So we use something a bit less here. Another consideration would be the life expectancy of the battery. After 10 years, the car is expected to keep about 70 to 80% of its battery power. Another way to figure out how many years could be by comparing the expected life cycles in kilometers or miles. So for example, here we have an expected 160,000 kilometers, and if you're going to do that over 5 years, then you may want to change the ownership to 5 years, as this is a fairly large impact on the economic evaluation of the vehicle. Now the next part relates to the actual driving conditions, and those of course can have an impact on the performance of either car. For example, if you're driving in an area that has a very mild climate, then it's not the same as if you have an area like Canada where you have hot summers and cold winters, which could be more taxing on the batteries. Also, of course, if you're driving an emergency vehicle, it's not the same as if you're driving a postal service type of vehicle. And if you're driving in the Rockies or in the Alps, then of course you're going to have a different performance. And so those different factors here would affect the real world losses. The manufacturer will give you a range and efficiency, but efficiency losses have to be fine-tuned based on the actual conditions. So let's say for somebody driving in Canada's national capital, Ottawa, then we could assume here those three conditions. Currently the model is not actually set up to automatically do the conversion of the losses. You have to enter that manually. The car manufacturers have a sticker efficiency. EPA provides another one. For example, here using the US government Environmental Protection Agency or the US Department of Energy data, we can compare the Honda Civic and Nissan Leaf and find out what the miles per gallon or performance of the car is based on their assessment. If you go to the Nissan website on the Leaf pages, they describe the range, which they show here 160 kilometers, but also explain that these may vary on different parameters, and they provide some examples which you could use to enter in the model based on your specific context. So for example, if you're going to have 2 or 3 months of very cold weather like we do in Canada, then you could use the for example, winter urban stop and go, which would reduce the range to about 99 kilometers instead of 160. And you would prorate that for, of course, the period of time that those conditions last. Using the model, you would then enter the autonomy based on the manufacturer's specifications and the battery capacity in kilowatt hours. And based on that, here the worksheet calculates the ranges of city and highway efficiencies based on the specifications, as well as here you can enter to the EPA. In this context here, with 160 kilometers, we'd get a combined efficiency of 0.15 kilowatt hours per kilometer. In other words, 15 kilowatt hours per 100 kilometers. When we compare that to the US EPA, we can see that the US EPA rating is quite pessimistic, where it actually reduces the performance. In other words, when the manufacturer tells you it takes 15 kilowatt hours to do 100 kilometers, the EPA tells you it takes 55, which is 3.6 times more. Going from 160 kilometers to 99 kilometers is about 38% loss, not 300%, and that would only happen for not even a quarter of the year. For this case study, we'll assume a 30% efficiency loss in real-world conditions for the ICE vehicle, and a 72% efficiency loss based on a requirement for heating of the seats in the winter, as well as air conditioning during at least 2 months in the summer, and maybe a driving style. Before we leave this section, I just want to point out also that the model contains some help. So for example, whenever you see a red dot on the upper right corner of the cell, that means there's a note with help. So if you point to it, then it will come up and give you some help. In a future version, we'll have hyperlinks that will provide more detailed information and link directly to some appropriate resources on the different cells. Let's now look at the energy model. Now you'll notice that throughout the model we try to use some color coding to be able to differentiate data that relates to the electric vehicle and that relates to the ICE vehicle. And so the ICE vehicle data is typically brown and light green for the electric vehicle. On the upper section, you can enter the fuel cost and the proposed increase for the fuel cost over the period of ownership. So the average gas prices have been, as of the end of 2010, in the neighborhood of $1.30 per liter. And in order to be able to figure out the escalation costs for energy, there's a number of factors. Of course, one of the factors would be to look at historical data, looking at the past. The thing is, the past is not always the best prediction of the future. I mean, if I was looking at the past here and extrapolate that, of course, I would have a very different curve compared to if I looked at it from this perspective or around here. So I think that it's very important that in order to predict the cost, you have a little bit of an idea of macroeconomics. And while the average increase has been about 10% here for the period that we consider, I would say that really would be important to do some sensitivity, because there is no certainty around that, and with the depreciation of the dollar, the US dollar, which is used to purchase oil, and oil being imported, then that can have a very major impact on the increasing price of gas at the pump, much more than potential new discoveries of gas or even the peak oil effect, I believe. So here I'll start with $1.29 per liter and a 10% energy escalation for the 10 years of ownership considered. Now for the electricity cost, what's very important here is that you look at the actual retail cost, including all the charges. If you look at an electric bill, there's a number of different things. Another factor to consider for electricity cost is when the car would be recharged. For example, in Ontario, they are time of use billing, and currently you pay a different rate at night compared to during the daytime. So in the context of this case study, we'll assume that mostly the car will be recharged at night during off-peak at 6.3 cents, and that occasionally it may be recharged in some other at work, for example, other places where if you have to pay for the gas, it may be a little bit more. So overall, we'll put that at 8 cents per kilowatt hour. Electricity prices are much more controlled than oil prices. They're quite regulated, and here we can expect a much lower increase in price. So we'll just leave that at 2%. Next, we'll go to the cost analysis, and we'll start by entering the tax. So in the case of Ontario, we have an HST, harmonized sales tax, which is at a rate of 13%. So here you can enter the formula for calculating the various taxes, the state and provincial or federal taxes. We can also specify if the incentive for electric vehicles is going to be applied before or after tax. In this particular case, you had $8,500 incentive. That's a difference of about $1,200, so it could make a difference. So we'll use the least favorable context. I'm not sure what it is in Ontario, but we'll use the least favorable context. Currently, the incentive in Ontario is $8,500 for 100% electric vehicles, and you may want to check. Sometimes there are different levels of subsidies at the state and federal level. There could also be some tax incentives that you could enter in there. Most car manufacturers charge for some type of delivery fee. So here we'll enter something similar, and you could also enter some other costs. For example, if you took an optional charger, you could for the electric car, you could add that there. Here we'll assume that we'll need that. We'll need a fast charge. We'll be happy just to charge at night. The next section allows you to enter your operating and maintenance costs. Those are your yearly costs. And one of the most important ones is the insurance. And there are a growing number of insurance companies that offer reduced rates for electric cars. Our course website provides some information about that. If you scroll down here, you'll see under the section 2, life cycle and maintenance cost. But since insurance actually accounts for a fair amount of the operating cost of a vehicle, we actually create a special section for that. The course provides also some other useful information about insuring electric cars and different companies that offer that type of insurance. Again, when you look at the summary here, the insurance cost is quite significant and adds up to being the actual second biggest expense for a car. Even in the case of electric cars, that could be more than the cost of the battery itself. We're not going to get into details over all the different type of operating costs, but obviously some of the costs will not be incurred by an electric vehicle. You will need oil change, tune-ups, and you'll have a reduced cost on brake pads since electric cars use regenerative braking. You won't need a transmission, mufflers, anything like that. The parking also, we put a special category there because there are more and more municipalities and areas where you can actually get free parking, and that could amount to quite a lot. Same thing with the tolls, special tolls for bridges or to get into cities, which you may not have right now, but over the next 5 to 10 years there's a possibility that those type of things could happen. We have assumed the same cost for tires and shock absorbers, and the model gives you in the end here some ratios that are useful to compare to industry standards. And by the way, if you want to be able to see what the average costs are, again on the website we provide a wealth of information about that. We reference a number of studies in the US and in other places, and studies from governments, universities, and professional organizations such as vehicles, automotive associations. The next section deals with the electric vehicle batteries, and the reason why we've done that is that number one, we want to be able to evaluate how much of the portion of the electric car is actually due to batteries, and second, we want to be able to evaluate how much that particular part will depreciate compared to the balance of the vehicle. Something else which is very important is to consider the residual value or the resale value at the end of the ownership. And in the case of ICE vehicles, typically you may only get 20%. Electric cars, because actually they have less moving parts, and the only part really that needs to be changed at the end of life cycle is the battery. In those cars, basically the body will actually keep proportionally more value compared to regular type of vehicles. So we can expect, while we don't have a lot of data right now, historical data, but we can expect that the resale value will be actually higher. There's a number of factors that affect the resale value. Of course, there's the market. For example, when some electric vehicles manufacturers stopped making cars, actually the cars' values went up because a lot of people were seeking those type of cars. So there's many considerations. Next, we'll look at the financial analysis worksheet, and this is where you can specify whether or not the car will be financed. I would very strongly suggest that you actually look at financing an electric vehicle. Currently we have fairly low rates, especially in Canada right now, for financing, and the amount actually financing is really quite small compared to other type of cost. So it's worth it to put that into the equation. And what that does, that actually makes your monthly cost fairly comparable. For example, here if we did not finance, then we'd have a much higher initial cost on the first year, and it would not really change very much the global impact on the financial attractiveness of the project. So I'll reset the value to yes, and we'll set that to a fairly high debt ratio of 95% with just a tiny little down payment, and we'll finance that over the maximum. Often regular cars are financed over 3 to 5 years, but in the case of electric cars, I would suggest you seek longer type of loans. We'll just use interest rates that are currently offered, and the inflation rate here is used to in the background to calculate things that increase over the period of the ownership of the car, such as operating and maintenance. The discount rate is used in order to calculate the net present value of the project and the ROI. In the area below, we can see the summary through the years. We're detailing here the internal combustion engine vehicle or fleet capital expansion cost with the financing, the capital, and the interest. And we're also showing the cost of fuel, So here it shows the total cost per year for operation, and on the electric vehicle we can see a higher cost for the capital cost, but of course a much lower operating cost. And in the end, we can see here the cash flows, and what we've done there in the summary is that we broke down the cost of the car and remove the cost of the battery, then put it back here in a separate category. So it's end up being the same, but just to be able to visualize how much that's worth. The emissions analysis worksheet allows you to look at the impact of carbon credits. So here we had put 15, we'll just set that at 0, but there's a possibility in the future that you may be able to get some credits, and we've seen actually prices going anywhere from about 10 to 30 or even more dollars per ton. So this is our financial summary. So here we can see the initial cost difference, the total cost through the life of both type of vehicles, and so here we're showing savings over the 10 years of $26,000, and when we use the discount rate to bring that to the all the cash flows to the initial value in this case at the end of 2012, that would be 18,000, and that is above the difference initial costs, which is why we have a benefit cost ratio favorable above 1 here of 157. And IR here, the formulas cannot calculate that because actually it's just too good. In some situations we rely on the worksheet functionalities. And now let's do a little bit of what if analysis here. So let's look at what if I wanted to buy actually a more high-end car such as the Tesla car. So let's just put the value here and look at what happens in the financial summary. Well, of course we don't get such good benefit ratio, but we still have possibility to recoup our money over time. So let's say if I compare it to a sedan model of $20,000, then we actually get a break-even around that period of time, but we can see that still we have an IRR which is not that bad. Well, I hope you enjoyed this presentation. GPEX is in the business of due diligence on different type of clean energy projects. So if you need some consulting for a car fleet, or if you want some training or consulting on renewable energy project feasibility analysis, make sure to go and visit our websites at gpex.com and cleanenergyeducation.net. Thank you.